This lesson is our first lesson on derivative graphs, and so we're just going to be talking about graphs of the original and the first derivative today. And the first thing that I want you to do is remember that the derivative is the slope of the tangent line. So I have a graph here, and I want to answer some questions about it. The derivative is the slope of the tangent line. So imagine drawing little tangent lines all along this graph and think about those slopes. Where would the derivative be positive? The derivative is going to be positive any place that that tangent line is pointing uphill, because a positive slope is an uphill slope. So any place that would have an uphill tangent line would be considered a positive derivative. So on our graph, we would be uphill tangent lines between A and C, and we would be downhill here, so then between E and F and after that, so I'm going to say from E to infinity, in fact, assuming these continue on forever, because this is uphill, all the tangent lines would be a positive slope. Okay, so the next question is, where is the derivative negative? And if you think about a negative slope is when you have a downhill line. And so where would you draw tangent lines that would be going downhill? Right, this first part, so from negative infinity to A, would be downhill, and then C to E is a downhill section, so C to E would be another section where we would have negative slopes of our tangent lines. It's downhill. Where would the derivative be 0? And if you think 0, that's a 0 slope, so you're thinking horizontal line. Horizontal line has a slope of 0. Where would the tangent line be horizontal, and the derivative therefore be 0? Okay, so again, yes, that would happen at A, at C, and at E, because at those places the tangent would be flat, would have 0 slope. So A, C, and E. Now, think about these things that we've just written and the characteristics of graphs that you've talked about before. The derivative is positive where the graph is doing what? Going up, increasing. The derivative is negative where the graph is decreasing, and the derivative is 0 where what's happening? Maxes and mins, right? Okay, so let's write those as fill in. Okay, the derivative is positive where f is increasing, where f is decreasing, the derivative is negative, and where f has a max or min, the derivative is 0. We're going to call this critical points, and we'll add to that definition later on in the course, but for right now, maxes and mins in our critical points. That's just a word that describes max or min for right now. It could also be a flat place on the graph. So put comma flat, because if you think about a flat place, the tangent line would also be flat. So maxes, mins, and flat places can all be called critical points. Now, we're going to start sketching derivative graphs given the graph of the original. And we have to think about what we were just talking about, the positives and negatives. We're not going to get incredibly detailed in our sketches today. We will get more detailed with more information later. But for right now, we're going to focus on the main characteristics that make that happen. So I want you to look at this original graph and think about the tangent lines and the increasing and the decreasing stuff, and tell me what you know about the derivative. And so in this first section between -3 and -1, we're going downhill. So what do you know about the derivative? It's negative. So I'm going to write negative for right here because it sometimes helps to write down what you're thinking. And then between -1 and 1, what's happening? You're uphill, right? So your derivative is positive. And then after 1, so 1 to 3, or 1 to infinity, it's all downhill, so the derivative is negative. Now, if you will cover up like this graph with your hands, cover this graph up and don't look at it, okay, and you know that this changed at -1 and +1, draw a graph that is negative and then positive and then negative. So if you covered up that original graph and you do a graph that was negative, positive, negative, what kind of shape did it have almost? Almost like a parabola. You were negative, then you were positive, and then you were negative. Now granted, I'm struggling with drawing lines, but it's a little difficult on here. Does that make sense? What kind of power is this graph over here? This shape is a x what? To what power? Cubed. And it's a negative because it's flipped. This is a negative x cubed. What is the derivative of a negative x cubed? Negative 3x squared. Is this a negative x squared graph? So that makes sense, right? Okay, that relationship between the original and the derivative is still holding algebraically and graphically. Alright, let's move on to another one. Okay, so let's focus on this blue parabola right here. Tell me what's happening with derivative on this part that's before 0. It's a negative derivative, so write that down. What is happening from 0 on? Positive derivative. Cover up the parabola. You know it splits at 0, which is, we've already marked with a y-axis over here. Cover that up and draw a graph that is negative and then positive. Okay, if you're negative before 0 and positive after 0, you can look like this. And again, that relationship. Here you have an x squared graph. The derivative of that would be 2x. And over here you have a linear graph. That makes sense, okay? The biggest thing that people do is they have a hard time looking at this graph and sketching the derivative graph because they're thinking so much about the other things happening here than the slope. And that's why I like for you to write it down and cover that graph up with your hand and sketch it so that you don't think about the shape of this graph and try to make that shape over here. It's not going to work. Okay, the next one is a line, and the derivative of a line, the tangent line here is the same everywhere. This one we can actually get a little more specific with and even get specific with today. Because, again, if you think about it, like let's say that this line was, and I don't even know what, we're going to figure it out in a minute. Let's say it was 5x plus 2. What would the derivative of that be? 5. And we could draw a specific graph. That is not the equation of our line. But if you think about what we just did, the slope of our line here is our y equals graph over here. So what is the slope of this line? Well, we went down 1, 2, 3, 4, and over 1, 2, 3, 4, 5, I believe. Okay, so what I'm saying is this point is 0, 3, and this point is 5, -1. The faint lines may not be showing up on your printed paper, but each half of a block is counting as 1. So if you'll just treat these like we know these points as 0, 3, and 5, -1, you can count. You would go down 4 and over 5. So down 4 and over 5 is our slope of that line. that means that over here our graph is going to be y equals negative 4/5, which is a horizontal line at negative 4/5. And so lines you can actually get very specific with right now. The other like polynomial graphs that we're looking at, we are not as specific today. Okay, so let's look at another polynomial, and let's again talk about what's happening. And you may even want to pause and try this one on your own. Write your positives and negatives at the top and mark your x-axis. So obviously it's going to change at negative 2 and 0 and positive 2 and about 3.5, we'll say. And then just work on shaping your graph over here. So pause and try to do your own graph. Okay, so if I'm looking at this, we would have increasing here, meaning that our derivative is positive till we get to negative 2. And then between negative 2 and 0, the graph is decreasing, so our derivative would be negative. Between 0 and 2, we're increasing, so our derivative graph will be positive. And then between 2 and 3.5, we're downhill again, so derivative would be negative. And then from about 3.5 on, we're uphill, so our derivative would be positive. So if I cover that up, I am positive before negative 2, negative between negative 2 and 0, positive between 0 and 2, negative between 2 and 3.5, and then positive afterward. And that makes sense because this looks about like an x to the 5th graph, and this is an x to the 4th graph. Okay, one of the things that I want you to notice while we're on this graph is obviously at negative 2, our tangent line would be horizontal and our slope would be 0, and that's why we go through negative 2 and have a 0 over here. So all of these zeros represent our critical points, represent our maxes and mins. You can tell by looking at this graph whether it was a max or a min, because when a graph changes from positive slopes to negative slopes, just like it did here, that's the top of a hill, because if you're going uphill and then you go downhill, you have a maximum. So I can look at the derivative graph over here and say, well, we were positive and then we were negative, so on the original you must have a max here. And then the same thing, when you change from negative slopes to positive slopes, you know, right here in the middle we had a flat horizontal line, so that derivative was 0. Again, that's why we have a 0 right here. But if you change from negative slopes to positive slopes, you have a minimum. So by looking at a derivative graph, if you change from negative to positive, then the original has a min. Okay, so you can know that just by looking at a derivative graph. Okay, I have 2 more, and these are kind of special cases that we want to look at. What is the first graph right here of? Like e to the x or a to the x. What is the derivative of that? Basically the same thing. If it's a to the x, you multiply by the natural log of a, but that's just a stretch. So again, if you think about the slopes, they're all positive. Every tangent line that I draw has a positive slope. But think about the steepnesses. Over here on this left-hand end, it's a positive slope, but it's not very steep. What is that slope close to? Close to 0. So close to 0 is what our slope is, but everywhere across this entire graph, it's all increasing, so it's all positive. So when we go to draw the derivative, we're completely above the x-axis. So let me bring this down for a second so we have a little more room. And you can make room on your paper, however. So we are completely positive. Everything that we draw over here should be above the x-axis because we are completely positive on this one. Now, then we get into slight details. Obviously on this one, because we're almost flat over here, our slopes are close to 0. So on this one, we're going to be close to 0 over here. The further we go to the right, the steeper they get, and so that means that the y values on this graph get higher and higher. And so just like we predicted, this derivative graph basically looks really similar to the original, but again, if this was e to the x, the derivative of e to the x is e to the x. You're looking at the same graph, but the slope relationship is still there. So this is kind of like a special case. The next one is an absolute value graph, which is basically two lines that meet at 0. Now, the slopes to begin with are negative, so our derivative is going to be negative. And the slope after that is positive, so our derivative is going to be positive. So we're going to be operating in the negative on this side and in the positive on this side. But just like the line that we did a minute ago, we can tell the slope of this. If this is the absolute value graph, the slope of this side is -1, and the slope of this side is +1. And it's -1 that whole time. So if I'm graphing this, I have a horizontal line at -1. And then I have a horizontal line at +1. Now, what's happening at 0? 0 is one of those places where I can draw tons of tangent lines and have tons of options, so the derivative is not defined. So at 0, even though it's a minimum, it's an undefined derivative because of the multiple tangent lines that I could draw. It's one of those not differentiable places that we learned about. The way that's represented on the graph over here is just by a jump where there is no derivative, there is no point with a derivative there at 0. So you would have a horizontal line at -1, an open circle on 0, then an open circle on 0 up here, and a horizontal line at 1, because everything after that and before that work, but at 0 it's not differentiable. Now we're going to go backwards. We're going to look at this graph over here on the left-hand side as our derivative graph. Okay, so what were we caring about a minute ago on our derivative graph? We were caring about whether we were positive or negative, and we were interpreting that over here. So since this graph is positive here and positive here, meaning it's above the x-axis, what do you know about your original? The fact that this is positive doesn't, we're not caring about whether it's increasing or decreasing, we just care about the fact that it's positive, means our other graph that we're talking about, our original graph, is increasing. So I'm increasing here and increasing here. Now, the derivative graph hits a 0 at 0, and so I need to keep that in mind and make the slope be 0 over here. So again, cover up this parabola so that you don't stress yourself out, and draw a graph that is increasing before 0 and increasing after 0, and has a tangent line at 0 that would be flat. Now, one of the things that bothers people about this is that we don't have y values. We don't know specifically where to put it, and that's okay. You'll learn that later. They'll give you that information later. For right now, are you increasing before 0? Is it flat at 0? And are you increasing after 0? So is your graph increasing, flat, and then increasing? Okay, again, with that graph, I didn't know where to put it. I was just looking to make a graph that was increasing, flat, and then increasing. I could have put it up there where I did. I could have put it down here. I could have put it up here. It doesn't matter right now. Later on we will get information that helps us figure out where to put it. Right now we're just worried about shape. Okay, moving on. Our second derivative, second graph on this page that is a derivative, is positive until about, let's say that again this is 1, 2, 3, 4. We'll say that's positive till about 4, and then negative after that. So I'm going to mark a 4 over here. And so again, positive above the x-axis means that our original graph is increasing, and then below the x-axis being negative means that our original graph is decreasing. So we want to draw a graph that has and is 0 between. So we want to draw a graph that's increasing and then has a horizontal tangent line and then is decreasing. And again, I highly recommend covering up this graph so that you're not looking at this particular graph. Okay, so if our graph is increasing, has a 0 and then a tangent line and then decreasing, again, I don't know whether to draw it down here or up here or whatever, but I need to be increasing before 4. I need to have a horizontal tangent line, so I need to hit a max. And then I need to be decreasing after 4. So you could have put that up, down, wherever. As long as it looks like an upside down parabola with a max at 4, then you have done it correctly. Alright, let's do another one. This whole graph is positive. What does that tell us about the whole graph of the original? The whole graph should be increasing. Now, we can get a little bit more specific because of what's happening on the ends. Because these are positive, we're still increasing, but they are close to 0 on the ends. So that means that our graph is close to flat. Because that would be how you would get a horizontal tangent line, or a tangent line with a slope of 0. We're not exactly 0, but we're pretty close. So stop for a minute, draw a graph that's completely increasing and is close to flat on the end. Okay, so again, I don't know where to put it up and down. I just need to make sure that the whole thing is increasing and I'm close to flat on the ends. And so I'm going to do something like this, where I'm close to flat here and close to flat here, but I'm increasing the whole time. It's probably going to resemble a logistic graph if you're familiar with a logistic graph. Okay, now these graphs here, what I want you to try to do is to take each one and look at it as if it was the derivative and sketch the original on that same axis. If you're still struggling with that, come over to the side and do it. But if you can, for example on A, I'm positive, so my derivative needs to be increasing. Then I'm negative, so my derivative needs to be, my original needs to be decreasing. Then my derivative is positive, so I would be increasing. And then my derivative is negative, so my original would be decreasing. So this is your derivative that's given to you. You're trying to draw the original somewhere right around that same thing, just so you can get used to looking at 2 graphs at once for what we're getting ready to do next. So pause and give it a shot. Okay, so again, it doesn't matter where vertically that your graph is, but you need the characteristics to be the same. So for B, we were negative and then positive and then negative, which means my original would be decreasing, increasing, and then decreasing. For C, it was negative, positive, negative, so again, decreasing, increasing, decreasing. For D, it was positive, negative, positive, so increasing, decreasing, increasing. And then for E, we were negative, positive, negative, positive, which would mean decreasing, increasing, decreasing, increasing. And again, I'm not getting totally specific, I'm just getting the basic shape going. So hopefully you did well. Okay, so now we are going to match. This is one of the things that you need to be able to do because sometimes you're given these graphs in a multiple choice type situation. And so if you read this question, the graph of the function a through d with the derivative in 1 through 4. So these 4 are the original and these 4 are the derivatives. Take a minute and see if you can match which one goes with which. Okay, so when I'm doing this, I like to look for the easiest thing first, and to me that is B, because you have lines and those become horizontal lines on their derivative because this is the same slope wherever. And so we should have a positive line and then a non-differentiable place, a negative line, a non-differentiable place, and then a positive line. So B matches with 4, and that takes 1 out. The next easiest one to me, well, they're kind of all polynomials, but it really doesn't matter, I guess. If we just start, if you're looking at the original, again, the tangent lines, or the fact that the graph is decreasing means that the derivative is negative. And then when it's increasing, the derivative is positive. And then it's decreasing again, so you're looking at negative. So look at what's left. Do you have anything that's negative and then positive and then negative? 3 is negative, positive, negative, positive. So it has 1 too many changes. 2 is negative, positive, negative. And so A matches with 2 because of that amount of changing. They do. Okay, the critical points, your maxes or mins, that's where the slope is 0, here and here. That means there's zeros on the graph down here. So that's where that graph is crossing the x-axis. So those match up as well. Okay, let's look at C. C is negative slopes, 0 slope, positive slopes. Okay, now on the ends it looks like it's almost flattening out, so it's getting close to 0, so we may consider that if we don't see an answer. But down here, the only 2 that I have left, it has to be number 1, because number 1 is below the x-axis, then 0, and then above the x-axis. So it's negative, 0, positive, so C matches with number 1. Now, why does D match with 3? Yes, we have the extra positive. So we have negative slopes, and then a 0, positive slopes, and then a 0, negative slopes, 0, and then positive slopes. So we have a 0 about here, at 0, and over here. So they have 3 places that on the derivative are 0. It's negative, positive, negative, and then positive. Okay, so we want to notice a few things. Where the original is increasing, so this dark red part, the derivative is positive, so this is light red. Then where the original is decreasing, the dark blue here, the derivative is negative, which is the light blue. And then where the original is positive, the derivative, or where the original is increasing, the derivative is positive. So again, the original is the dark red, it's increasing, the derivative is the light red, it's positive. So this is just another representation of that relationship. And again, I wanted to point out, you know that you have a max whenever the derivative changes from positive to negative. You know that you have a min if the derivative changes from negative to positive. If it doesn't change, which is what happens at 1, that means it's just a flat place on the graph, because negative, negative would mean decreasing, decreasing, and so you would have a flat place like this. If it was positive, positive, which we have one of those, you would be increasing, flat, increasing, and you would have a flat place. So a change from positive to negative means a max on the original. Change from negative to positive means a min on the original. And again, this is when you're looking at the derivative. The last thing that you need to be able to do is to pick which is the original and which is the derivative in an image where they're on top of each other. And so you can do that sometimes by looking at powers for like the first one. The blue looks like an x cubed graph and the red looks like an x squared graph. And so you could probably say that the blue is the original and the red is the derivative. But you can still look at the fact that where blue is increasing, the red is positive. Where blue is decreasing, the red is negative. That can be useful too. And sometimes, things look really mixed up like this last one over here where you're not able to do that. You may still be able to do powers here because the red is kind of W shape, which is like x to the fourth, and the blue is kind of cubic shape. And so the red is probably the original and the blue is probably the derivative. But you can again check those slopes. Where the red is decreasing, the blue is negative. Where the red is increasing, the blue is positive. Where the red is decreasing, the blue is negative, and where the red is increasing, the blue is positive, so those do match up in that relationship. This last one isn't as polynomial-esque to figure out as far as powers go algebraically, so you really need to look at those slopes. What I recommend is just picking one. So if I pick the blue one, I'm going to say, okay, if it's increasing, then the other one should be positive. So I'm increasing here, the other one is positive, that worked. I'm increasing here, the other one's positive, that worked. And I'm increasing here, the other one's positive. So it looks like the blue is going to be the original and the red is going to be the derivative. If you had chosen the red to start with, the red is decreasing until you get to this x value right here, and the blue would be negative until that x value if the blue were its derivative. And it's not. It hits this little positive space. So you can tell that the red is not the original based on the increasing, decreasing, positive, negative relationships that we look for. And that concludes this lesson.